Now, if you go back to how we defined ds, and by the way, ds is all over the next course. If a curve C is defined parametrically by x to being a function of time and y being a function of time, right? And I want to find the length of the curve from A to B, there's no need for me to say L equal the square root of 1 plus f prime of x squared, or the square root of 1 plus g of y prime squared dy or dx anymore. Instead, all what I'll do, I will simply say, and if you look back at the way we derived this back in chapter 8, take that back, I'm in chapter 6, 6.3, I derived that. You could look at the derivation, and instead of dividing by dx, both sides, and proceeding or dy, just divide by dt and everything matches. No need to derive this. So basically, ds now is the square root of f prime of x squared g prime of y squared, assuming that that's the x, that's the y. And let's look at a couple of problems. And if I look at a couple of problems, oh, this is out of sync. There we go. If I look at a couple of problems, one of them is number 26. It says find the length of the curve, L equal the integral of ds, something that you should really get comfortable with. It's the integral from 0 to radical 3. You'll notice here, things are a lot simpler. I don't have to think much about which way to go, because dx dt is 3t squared plus dy dt. If I bring the power down, that will be 3t squared dt. And I'm assuming you could integrate that. We just learned techniques of an equation. And I'm going to set up 3 more problems. One for length. Same idea. Here we would say L equal the integral of ds. That is the integral. And again, no need to worry about which direction should I do this with respect to x or y. It doesn't matter, because x and y are in terms of t. So if I take a derivative of, and this is really saying 2t plus 3 to the 3 halves 1/3. By bringing the power down, the 3's cancel out. You get 1 half. You know what? I don't know why I'm cluttering this. Let me go in order and let me go slowly. So it's going to be, bring the power down, 3 halves cancel out, 1 half 2t plus 3. Subtract 1 from the power, that is 1 half. And you get to square that, plus the derivative of this, that's 1 plus, bring the power down, subtract 1 from the power, and there it is. That would be the setup. When I say on a test setup, do not solve, that's all I want. I'm assuming you could integrate anything, right? Alright. And if you remember correctly how this works, if I want to find the area of the surface of revolution rotated about the y-axis, s equal the integral of 2 pi x ds. Again, we had the same problem last time. We started with this, figuring, well, okay, let's see how that works. Here, we don't have to do that. If we look for the surface of the area of revolution, that's the integral of 2 pi. So I know automatically, since it is rotated above the y-axis, x is right there. No need to worry about whether I leave it or eliminate, because everything is in terms of t. And if I take the derivative of that, that will be t to the 1 half squared, plus the derivative of that, that will be 2 times 1 over twice the square root of t squared dt. And there it is, integrated from 0 to radical 3. That will do the trick. And if I look at number 34, we know that rotating about the x-axis, s is really the integral of 2 pi y ds. And again, here we don't have to worry about figuring out whether to leave y or not. Well, one, I know it's from 0 to radical to pi over 3, done. And I know what y equal. Y is right there. Everything is a function of t. So it's a lot easier using parametric equations to really figure out all of those. Dx dt 1 over the secant of t plus tan of t times the derivative of secant, that's secant of t tan of t, plus tangent squared of t, plus, I forgot one more piece, minus the cosine of t squared, and derivative of cosine is negative the sine of t squared dt. I do want to clean one thing up just to make sure you're seeing this. This is the integral 0 to pi over 3. 2 pi is a constant, cosine of t, square root. I do want to point out, if I factor a secant, if I factor a tangent of t out, I'll have a secant of t plus tan of t divided by secant of t plus tan of t. Just want to point that out. And you notice those cancel out, and you can proceed and finish up the problem. And that's pretty much it. And there's the homework associated with this section.